Hello. So this is a conversation on proofs. So there's three different proofs that we're going to be looking at today, which are going to be the vector spaces, the subspaces, and the linear transformations, and how their axioms functions along with their similarities and their differences. So the one thing that makes the vector spaces different is that they got a lot of axioms, and it has to pass each one in order for it to exist. The next thing that makes it different is that it also has these, which are the four elements that describe it, which are the main subset, the element, and then the two, which are typically just addition and scalar multiplication, which allow this to occur and this to occur. Without those two, those would not be valid, and it would fall as invalid. The little example I drew out is that I would just create random vectors with random values, and I would run them through. So V just is the subset. U I described as 0, or as the 0 vector, which is just the row of zeros, or whichever you require. After vector spaces, we have subspaces, and what makes these a little bit unique is that we first start off by checking if they are not empty, and also that it is a space within a vector space. So just a small dog inside of another small dog. I thought that was gonna be funny, but it's not as funny anymore. The example I used is similar to the first example, was I just picked x and y vectors to give me my spaces. And I simply ran them through their test, which in this case A is just A1 from vector spaces and S1 from vector spaces, along with checking if it was non-empty, and it is non-empty because all of these are just random numbers, so they could just all be 0 at some points. The last one is going to be the linear transformations. So linear transformations still come from vector spaces, and they are still taken from axiom. No, not axiom 1, my bad. It's going to be the scalar of S3, I believe. And it's also going to be S1 as the previous one. So what a linear transformation is unique is that it takes components from one vector space and takes it to another vector space. So that's why we have u1 and u2 over here, because those components, or say for instance it could be like a column of u1 and a column of u2. So it'll take those two u components and whatever's in those u1s and u2s and would move it to t and make it a function with that. And the second one is just using a scalar and multiplying it to the system. So for my example, I used u as my subset,